Hi, my name is Georgia Hilburn, and this is my draft for the second FEA project, Designing for Frequency. At the bottom of the slide, you can see my final design, which will be discussed later in this presentation. The objective for this project is to design a piece of PMMA plastic for 3 different testing scenarios. First, it must have a natural frequency of 2 Hz. Second, it must be able to withstand a static cantilever beam load of 50 grams. And finally, it must be able to withstand a static tensile load of 2,000 grams. The dimensional limitations and material properties for this design project are as follows. First, our design is bounded by a 150 by 150 millimeter square piece of PMMA acrylic cast sheet. The thickness of this sheet is 2.54 millimeters. Our design must be at least 100 millimeters in length and have areas for the pads of the clamps to sit on with a diameter of greater than or equal to 16 millimeters. Additionally, there must be a hole for the weights to hang through of equal to 6 millimeters. The properties of PMMA are as follows. The Young's modulus is 2.798 gigapascals. Poisson's ratio is 0.37, the tensile yield strength is 60.65 megapascals, and the density is 1.19 grams per centimeters cubed. The diagram of the cast sheet we'll be cutting from is seen in the center. It has side lengths of 150 millimeters, and the diagonal is 212 millimeters, which is important to note for the discussion of my dimensions and my final design later in this presentation. Discussing my dimensions, I want to talk about how I optimized my design via structural mechanic equations and trial and error. On the left side of this page, you can see equations for deflection, bending stress, tensile stress, the second moment of inertia, and the factor of safety. I plugged these equations into Excel, adjusted the width and length parameters, and was able to optimize my actual design geometry based on data that I gathered from ANSYS. I decided to use a dog bone, and while it's possible to use other geometries, I really wanted to figure out how the width and the length actually affect the frequency of my design. I was able to determine an equation for frequency based on the beam geometry or dog bone geometry, and this was determined via linear regression. I adjusted the width and length of my dog bone design, plugged it into ANSYS, and analyzed the frequency of the object, plugged these data points into this graph, and were finally able to compare the length and the width of the different designs. As you can see, the only 2 designs that were able to achieve a frequency of 2 Hz were the 190 millimeter length dog bone and the 160 millimeter length dog bone. The 190 is marked in the red lines. However, if you go towards the deflection versus width graph on the right, you can see that with a width of 6 millimeters and a length of 190 millimeters, this design would experience a deflection of 5 centimeters. On the other hand, the 160 millimeter length and 2.5 millimeter width would experience a deflection of 7.5 centimeters. Overall, I learned that by maximizing the length, I would minimize frequency but increase deflection, while on the other hand, maximizing width would minimize the deflection but increase frequency. These are the dimensions of my final design. As I discussed previously, I decided to go with the 6 millimeter width and the 190 millimeter beam length, which is the length from the center of the clamp to the center of the applied force. The total length of this design is 210 millimeters, which is less than the diagonal of the acrylic sheet that we're given to cut from. Additionally, the pad areas have a diameter of 20 millimeters, and the radii of this dog bone are 30 millimeters in radius. Finally, the hole is 6.5 millimeters with an extra half millimeter added to ensure that the weight can fit through. To analysis. Modal analysis predicted that the mode 1 natural frequency would be 2.08 Hz, which is really close to our expected frequency of 2 Hz from our Excel analysis. The setup on the left shows that we have one fixed end shown in purple, we have gravity applied as a body force, and we have the distributed mass applied at the bottom face in red, which is the shake weight of the phone and the clamp as described by the project requirements. The total range of frequencies in different modes is shown in the table on the right. The tensile loading analysis predicted a maximum stress of 1.35 megapascals and an average factor of safety of 15. The setup is shown on the left, with the fixed support shown in purple, and we have the body force applied via gravity, and finally the 2,000 gram weight hanging from the hole shown in red, which is about 20 newtons. Next, our bending loading analysis predicted a maximum stress in bending of 11.2 megapascals. This setup is shown on the left with, again, the fixed support shown in purple. We have the body force applied via gravity, and finally the 50-gram weight applied on the right side in red. This is a force of about 0.4 newtons. The minimum factor of safety of this design is 5.42, which occurs next to the max stress as expected, and the maximum deflection expected by this design is 3.67 centimeters, which is a little bit less than the expected 5 centimeters from our Excel analysis. But not least, we refined the mesh via convergence and achieved within 5% for both static analyses. On the left, we have the convergence for the tensile loading, and on the right, we have the convergence for the loading and bending. And in fact, both of these actually converge within less than 2%. That's all I have for today. Thanks for listening to the draft of Project 2, and I look forward to a great experiment.